We'll get started promptly on time and we will finish up a few minutes early. I know there's a thesis defense in the Wong building that starts at 10. I happen to be on the committee, so I want to make sure I get over there as quickly as possible. So we'll end a few minutes early, so we'll start right on time promptly here. Few quick announcements. Firstly, next week, Tuesday, will be our first guest lecture from Josh Figueroa, our neighbor at UCSD. Josh, I gave a great talk on fundamental inorganic and organometallic chemistry and some of his group's research. It's a great lecture every time we've had him, so really looking forward to that. That will be in person, so please make every effort to attend in person if you can. We'll have some guest lectures later this semester that are fully virtual, and we'll give you the option to take it from the comfort of your home or office or here, but the ones that are in person, please make every effort to attend in person. Homework set is available, and the first office hour is scheduled for May 2nd. That's next Friday, and the time is
1 p.m. Pacific time.
1 p.m. Pacific. Okay. And as I said last time, please make an effort to at least spend 5-10 minutes looking over the problem set this week, so you have a sense of the lay of the land and the types of questions. Any administrative questions before we jump in? Last time we left off with a discussion of oxidative addition, so we'll pick up right where we left off and continue marching our way through elementary steps. If you're following on the syllabus, we just tweak things slightly. So we'll try to wrap up the elementary steps discussion more or less today, and then we'll have Josh's lecture on Thursday. Tuesday, Thursday, we'll do any last minute wrap up that's required, and then we'll shift into carbines and we'll be off to the races then in terms of catalysis. As I mentioned, there were a few specific dates and times of guest lecture for the second half of the semester that'll be finalized this week. So we'll have a truly final version of the syllabus that we'll post that you can consult by next Monday. Okay, we'll jump in then. We left off last time with problems of the day for folks to take home and think about. So we'll just jump right in here. The first one, so these are ask you to compare pairs of complexes and order them with respect to which is more likely to undergo said reaction, given reaction, faster. So for A, let's take Catherine. What do you think? So the reaction is an oxidative addition. Yep. It's an isostructural pair, rhodium versus iridium. What is on the periodic table, what's the relationship between rhodium and iridium? Perfect. So we have the second row versus third row. Everything else is the same. So which would you be inclined to think? So in oxidative addition, is it going to be more or less favorable, or is it going to be more favorable with a electron rich or electron poor metal? More electron rich. And so which between rhodium and iridium do you think would be preferable in this oxidative addition? Iridium, okay. What are your thoughts there? So we talked about electron richness. That's one consideration. Anything else?
polarizability.
Okay, polarizability. So that's a good way to think about it. So we said that in terms of size, second and third row end up being similar. So there might not be a big difference there, but polarizability is an interesting one. That's basically you're saying that the metal is holding its electrons in more diffuse orbitals. That goes hand in hand with nucleophilicity, electron richness. And then remember, comparing second row is going to form a stronger bond to carbon. That's a thermodynamic argument, but if we invoke a late transition state, then you would say there's also transition state stabilization, so you get kinetic benefit as well. Any questions on that? Thank you, Catherine. 2, Al, what do you think here? We're comparing oxidative addition of in BiNAP ligated palladium zero complexes. In one case, it's bis BiNAP. In the other case, it's BiNAP DBA.
Well, I have kind of two conflicting arguments, I guess. And one is that one is the phosphine ligand, which have been shown to help increase the rate of oxidative addition.
Okay.
But also I feel like it's very sterically hindered compared to DBA.
Okay, maybe let's start out with just doing a quick electron inventory on the starting material in the case of the BiNAP. So let's play this out. So we've got palladium 0 is what?
D10.
Palladium 0 is D10. And I don't have this drawn out in any, I guess on the worksheet it's drawn in a more suggestive way, but I'll tell you that BiNAP's coordinated bidentate here. So
4L type ligands.
4L type ligand.
With 18 electron complex.
8 electrons for overall total of 18 electrons. So for oxidative addition to happen, what needs to happen first?
Oh, we could dissociate one of the, I guess the bidentate ligand as a whole. And if you want to dissociate that, maybe the sterics of that phosphine ligand will help it be more favorable.
So to get to the, so if I understand what you're saying, you said to get to the reactive form, we need to lose the ligand. But, and then in this case, if we lost bidentate, we lost both arms, it would be really reactive, 14 electron. Maybe there's a solvent molecule there or something to make it 16 electron. And then that's going to be the reactive form that participates in oxidative addition. And then what was the rest of your argument, Al?
One is the sigma donation of phosphine, helping the palladium be more electron rich, which
Okay.
helps oxidative addition.
You're saying if, like, let's say only one arm of the BiNAP dissociated in your 16 electron and you've got the phosphine kicking in electron density, then that would be more electron rich than DBA.
Yes.
DBA, again, it's not, I don't really provide much information here. You could imagine this drawing, coordinating in a monodentate fashion through one of the olefins or through both. I think the reality is it's just coordinated through one. What properties does DBA has as a ligand?
It's hemilabile.
And, it is hemilabile, but in terms of, do you consider this a strong sigma donor, pi acceptor?
I think it's a pi donor.
Pi donor. What characteristics do pi donor ligands have? They normally have lone pair on the bonding atom.
And I guess in the case of the oxygen atom having that basicity.
Okay, so let's draw it like this. So if I tell you that
Oh, no.
DBA is drawn this way, what would you say about it as a ligand?
It's a strong pi acceptor.
Okay, weak sigma donor, strong pi acceptor. Palladium is in the 0 oxidation state. It's quite electron rich, so it's going to form a strong bonding interaction with that DBA. And then if you play this out, then you're thinking that bonding interaction strong, dissociation of the ligand might be slower. For DBA, palladium binap is it's bidentate, but it's electron, it's sigma donating, the metal's already electron rich. It's quite sterically congested because it's tetraphosphine coordinated. If you actually looked at a 3D model, you'd say like, wow, it's really crowded. So it was happy to get off. So you've got multiple arguments in the same direction here. So what would you vote?
I feel like the steric argument of binap would help labelize that ligand off, which helps set it off for oxidative addition more than the TBA one would.
Okay, so you're saying, yeah, the steric bulk is going to push the equilibrium to the monoligated state or the binap ligated state. That would be the reactive form, and then we're off to the races. Okay, anybody get a different answer?
I just had a question. So for ones like this where you do need a dissociation first, do you like, I know that you could still get mono coordination with the bidentates, but like, is the primary like a driving force or like since the rate determining step involves dissociation, should we only be looking at how easy it is to dissociate versus like the donor characteristics?
Yeah, I mean, again, this is one where I think it's meant to be a little bit thought provoking and potentially force you to wrestle with conflicting
Okay.
messages.
Yeah,
So
that makes
I
sense.
think if you're weighing the relative importance of bidentate coordination versus sigma donation, I think you're weighing the right things. And it's meant to spark some discussion. Yeah, Eugene,
Wait, so what was the answer?
by now. And the explanation would be that it dissociates more readily as compared to DBA, getting to the reactive 14 electron form as drawn here.
Thank you.
Yeah. You have a question?
I was gonna say, can I try C?
You want to try to see? Okay, go for it. Oliver, what do you think? So first step, we have this dihydride, we're going to shine light on it. What do we think is going to happen first?
Iridium 0 is D9, sorry.
So we're starting with iridium 3.
So iridium 3 is 6.
Oh yeah, okay, so I see what you're doing. Okay, yeah, so iridium 0 is D9, iridium 3 is D6.
12 from the ligands.
Okay.
It's just 18 electrons. So before it does anything, it's to get excited up into that anti-bonding. Then it's got one available. Then you want to donate electron density into the complex for it to do anything. So if it's more electron rich, it's gonna be quicker. So that the E-fold side chain is gonna be.
So let's just focus maybe first on what happens when you, on this dihydrido iridium, you shine light on
Right,
it.
so
What do we think will happen?
You can go up to iridium 4.
Okay, so you have a metal to ligand charge transfer, and then
That'll start with the
and
CP.
then is it happy in that state, or is there any unimolecular process that it could engage in to relieve its energy? We talked in the ligand dissociation or ligand exchange lecture about this property of light and being able to promote what is called photodissociation. And through a somewhat analogous process, an excited state form, so let's say you described it as iridium 4, or you can just call it iridium 3 star, excited state iridium. It could lose a ligand, but it can also undergo another unimolecular process. I'll draw it here in a suggestive way.
Yeah. Does that electron go up into the proton and make a hydride and then it loses hydrogen?
So if we thought of this and as iridium 4, which I think it's reasonable to think of it as iridium 4. Then you'd say at a higher oxidation state, we haven't covered this exact part yet, but at higher oxidation states of a metal center, reductive elimination is favorable, just like when you're at lower oxidation state and have a more electron-rich metal center, oxidative addition is favorable. The microscopic reverse is also true. So let's say you're up at a, something that formally you could describe as iridium 4. That would make reductive elimination more likely. You have these two tempting hydridoligands that can react to lose H2, photo-induced reductive elimination. Now you're hot to trot, you have a really reactive 14 electron species. And I think you said, next, what do we expect will happen?
So then you're gonna get oxidative addition.
Beautiful.
Is it oxidative addition though?
You're going to form initially a sigma complex. With the CH bond. Sorry, that's drawn straight away. Of the incoming alkane, and then you said oxidative addition will happen next. Could also be described as CH activation via an oxidative addition type mechanism. So mechanistically, we've got a good idea here of what's going on. And then which did you favor, ethane or butane?
So just what's more electron rich?
That's one way you could think about it. Certainly, if it was a radical-based mechanism, you'd be thinking about which CH bond is more electron-rich, which is weaker. This is a closed shell pathway, and one of the things we learned about in oxidative addition is it tends to be very sensitive to sterics. Pretty much all oxidative additions that are inner sphere are quite sensitive to sterics, and that makes sense if you think about the energetic penalty of bringing an encumbered bond into close proximity to form the sigma complex in a metal center. So which do you like then, ethane or butane?
Ethane.
Ethane, good. Riku.
Why after the first reductive elimination, the iridium stays at the iridium 3 oxidation state?
Well, I think what we had, there might be a different way to maybe draw this out. I think Oliver had said that there's after irradiation, we will get to some iridium 3 excited state form that could potentially be described as a iridium 4 with a ligand centered spin.
So
It'd be
is it
like
just
a
the one is
ligand
considered
minus,
and the other is protic?
what's that?
Is it just one is considered hydridic and the other one is protic, and therefore when it attacks that, it kicks back the electrons in? Just stay.
No, I would just think of this as you, I mean, they're equivalent H's, so I don't think it's accurate to say one is more hydridic or one is more protic. I think it's basically you're getting to you could think of it as a ground state destabilization argument. You're getting it to an excited state. It's more reactive to do almost anything. And one of the things it can do to relieve its excited state energy is reductively eliminate, if that makes sense. Good. Any questions on either of those three?
The
Anna?
oxidation state of the iridium, is three, like, after reductive elimination. So,
Good catch. Sorry about that. That's what Riku was asking. Sorry. Okay, I understand. I thought you were asking about this iridium 4 thing. Sorry, that was a typo. Thanks for catching.
P16 electron. No.
Thanks for catching that. Perils of using the copy and paste feature on Notability. All right, any questions on that? We got a nice preview then of this next elementary step and next batch of notes, which is about reductive elimination. As I said, I'll go through this quickly because it's the microscopic reverse of oxidative addition, and many of the trends are the opposite of what we just saw. An interesting sidebar on this is that those of you who are familiar and have run cross couplings will appreciate that they involve oxidative addition and reductive elimination. And those two steps have almost diametrically opposed electronic requirements to metals. So a ligand that's good for one is often bad for the other and vice versa. And so this poses an interesting ligand design conundrum. So we just saw this. Actually, I think the previous example illustrates this very well, that upon, and I thank you again for correcting me, upon reductive elimination, the coordination number is reduced, and so too is the oxidation state and total electron count, as well as the d-electron count. So if we were to do the electron counting from the 16 electron 2 coordinate iridium 1, we would say it is now D8. Reductive elimination has strict stereoelectronic requirements in that in a classical concerted pathway, the two outgoing ligands need to be in a cis-oid orientation. And I think this is a common, we call it like a trick question that you get in problem sets or midterms where you're asked to compare rates and you go through all of the trouble of electron counting and think about this, that, and the other. And really it's just that only one of the two forms is reactive because of the underlying molecular geometry / stereochemistry. What promotes reductive elimination? It's mostly, first approximation, the opposite things that promote oxidative addition. So low electron density on the metal, including getting to a higher oxidation state. When I was a graduate student, one of the big challenges that people were in the field of organometallic catalysis were interested in is CF reductive elimination from palladium centers, for example. And one of the strategies that was pursued at that time and developed by Melanie Sanford's group and Jin's group and others was when reductive elimination from the palladium 2 oxidation state, CF reductive elimination, for example, is difficult, you could go to a higher oxidation state. You get to palladium 3 or palladium 4, from which reductive elimination of even the most challenging bond combinations or atomic combinations is more facile. Sterically demanding ligands are hypothesized to promote reductive elimination through this phenomenon we describe as squeezing out. And along the same lines, wide bite angles, chelating structures can have a similar effect. And then in terms of parameterization, this can be described, and we'll talk about this more in the ligand design lecture. Large cone angle or percent buried volume are different descriptors to quantify how bulky a given ligand is. Reductive elimination is typically easier with outgoing ligands that have higher amounts of S character in terms of their orbital hybridization. So this tracks with intuitively, if you're well versed in the cross-coupling literature and you read an introduction to any of the papers published in cross-coupling in the last 5 to 10 years, they typically start with something like, whereas CSP2 or CSP2 CSP couplings are relatively well precedented. It is harder to engage CSP3 hybridized coupling partners. Now, of course, there are a number of different radical strategies for doing that, but in general, by a classical inner sphere concerted mechanism, outgoing ligands with higher S character are easier to reduce. And that really goes hand in hand with the fact that those orbitals are more spherical in nature. So if you think about the analogy I like to make, and every once in a while people will give me a courtesy chuckle, of is that if you think about my chest as the metal and my two arms are the outgoing ligands. If you can imagine, I've got two beach balls that I'm holding. It's much easier to bring those together than if I've got two pool noodles that I'm trying to bring together. Okay, no courtesy laugh this year, but I swear I've gotten courtesy laughs in previous years. Spherical orbitals are easier. Reductive elimination, the whole name of the game is orbital overlap. So you need to form that incipient bond, and the less you have to distort the geometry to get there, the easier it is. In practice, and I think this was nicely alluded to by Oliver, is that in practice, when you have two ligands that are non-equivalent, so we just saw this case of reductive elimination of H2, those are two equivalent ligands. But when you have two that are equivalent, then often one will serve as the quasi-nucleophile and one will serve as the quasi-electrophile. And so if you're, for example, tracking aryl nitrogen reductive elimination rates, in that case, the aryl group will often serve as the quasi-electrophile, and the nitrogen ligand, the amido ligand, will serve as the quasi-nucleophile. And so in that case, more electron-poor aryl groups are being reductively eliminated faster. But it's not always obvious a priori which of the two outgoing ligands is behaving as a nucleophile or behaving as the electrophile. So sometimes those electronic trends can be a little bit difficult to predict and sometimes even difficult to back rationalize. It has been shown empirically that reductive elimination is often more favorable from odd coordination numbers. So if you're square planar, 4-coordinate, reductive elimination will often, not always, but often proceed via association of a ligand, for example, a pi-accepting olefin ligand, to get to a 5-coordinate state from which reductive elimination is more facile, or dissociation of a ligand to get to a 3-coordination state. And one of the working mechanistic hypotheses that if you want to read more about, you can direct you to this reference. It's computational, but still has some very nice illustrations at this point. One way in which this is explained is that reductive elimination from 3-coordinate or 5-coordinate metal centers, intermediates, both 3-coordinate and 5-coordinate have in common that they're trigonal in nature, trigonal and trigonal bipyramidal respectively. And in a trigonal geometry, we talked about Jahn-Teller distortion, through Jahn-Teller distortion, you will have some symmetry breaking. So 3-coordinate species will typically, through symmetry breaking, want to be Y-shaped or T-shaped. And in a Y-shaped geometry, you see that two of the ligands are brought in close proximity. And indeed, that can facilitate their reductive elimination. Now, one ongoing question is, I would say, reductive elimination, even though it's in the elementary steps lecture, meaning that it's seemingly well studied, it's still a topic where there's new truths to be learned. And I think one is that how these different, what the relative importance of these different properties are. For example, if you really bulk up a ligand, are you promoting reductive elimination by truly the squeezing out effect, or because you're promoting a lower coordination number prior to reductive elimination, or because you're inducing strain? And all of these are not totally equivalent. So I would just direct you, there's a really thought-provoking paper from Bill Morandi's group, a preprint in Chem Archive, just from 2 weeks ago. In the final version of the notes, I'll add a DOI here, but I don't have it handy. That seeks to map the interactions among these multifarious effects and their relative importance, and it points to electronic properties being the driver. So even sterically bulky ligands, their predominant effect on reductive elections is by through their contribution to electronic character. I won't say too much more about that. It's not been peer-reviewed yet, but is a really nice study that just illustrates that this is something that that the community is still wrestling with and trying to understand. I gave a prelude to the fact that some reductive elimination events are more difficult than others. We talked about CSP3, hybridized fragments being relatively difficult, and heteroatoms are difficult as well to reductively eliminate. They sometimes require special strategies like especially bulky ligands or getting to higher oxidation states. And there are a couple of reasons that you could think about for rationalizing this. One is that these atoms, nitrogen, oxygen, fluorine, all have in common that they're quite electronegative and they have relatively small and non-polarizable orbitals. And so if we're talking about orbital overlap being the name of the game, it's hard to achieve orbital overlap with atoms that like to hold their electrons very tightly. That's one issue. And then the other is that in these Y-shaped intermediates, the heteroatoms tend to like to be at the tip of the Y, not the V of the Y. And the reason, it goes back to this argument that we made before about how in trigonal geometries that the equatorial, those tend to be quite basic positions, electron-rich positions. And so the electronegative atom likes to get to the tip of the Y shape rather than the other positions because these are often pi donating ligands. Mechanisms, I think we've started to build this framework already. So from octahedral, a common mechanism is dissociative. And then one that we won't cover in too much detail is SN2 type. This is the direct analogy to an SN2 type oxidative addition. From square planar, I mentioned some of the options. If it wants to go through a odd coordination number, then it can associate a ligand or dissociate a ligand. And then there's also the possibility for a non-dissociative pathway. And then when you need to reductively eliminate groups that are preferentially sitting trans to one another, then you have an added barrier that you need to navigate, which is a cis to trans isomerization. Okay, let's take a look at a seminal example, seminal report from 1980s. This is from the pioneering organometallic chemist David Milstein during his tenure as a research scientist at DuPont, actually. So let's walk through this example together. First, let's take a look at the electron count of the starting material. Anybody want to help me with this one? Coordination number, it's octahedral, so obviously the coordination number is 6. Rhodium is in what oxidation state here? 3. B6, 18 electron. Okay, so right there is giving us some kind of clue that this is relatively stable electron count. So what happens next? We lose a ligand. Now we're at coordination number 5, 16 electron. And upon loss of this trimethylphosphine ligand, now you have a 5-coordinate geometry that will start transforming, relaxing into a distorted trigonal bipyramidal geometry. And then in that distorted trigonal bipyramidal geometry, you have this possibility for the 3 equatorial ligands to be in a Y-shaped orientation. which pushes the, remember we said that the electronegative atoms want to be at the tip of the Y, and that pushes the other two hydride and alkyl ligands closer together, promoting reductive elimination. Then reassociation of the phosphine ligand gets you back to your product. Doesn't get you back to your product, gets you to your product complex, coordination number 4, rhodium +1, D8, square planar, 16 electron count. Any questions on that? Oliver?
Say the ligand just falls off or it dissociates, what actually is encouraging it to do that? You just hate it, it just comes off.
Yeah, so one of the, it's a good question. So it's drawn here as in equilibrium. So you can imagine that for almost any metal ligand bonding strength, there's so let me rephrase this. If the metal ligand bonding strength is below a certain threshold, then in solution and equilibrium, there will be some population of the bonded and some population of the non-bonded. Now, in this study by Milstein, they part of what supported a dissociative pathway is they found that addition of exogenous trimethylphosphine suppresses the rate of reductive elimination. And that would be hard to rationalize if you had only a non-dissociative mechanism or an associative mechanism. That piece of data, add more phosphine, product formation is slower, is hard to rationalize with any other pathway. But it does tell you that under the reaction conditions, that there is a way to push this equilibrium farther this way. And then, as you said, if you heat the reaction, then this equilibrium, you can shift this equilibrium to the right, presumably that because you're going from a one molecule to 2 molecules, there's an entropic term that you can promote by heating. So I think that's a reasonable hypothesis for how you would drive that forward. Questions on that? Riku.
How would you monitor a rate reductive elimination?
Okay, how would you, if I just told you to do it, how would you do it? I gave you no further guidance and said, here's this complex, measure reductive elimination rate. What would go through your mind?
So like you mentioned about like the addition of trimethylphosphine should suppress the reaction
Yeah.
because we needed to lose it first.
Yeah.
But how would you, can you just isolate that complex on the left?
Yeah, so this is isolable.
I see.
So this is, you can mass this out on the balance. We'll talk about later in today's class, some more transiently stable species that need to be generated in situ, but this is an isolable complex. So you can mass it out and then you can choose your favorite analytical technique for monitoring either consumption of the starting material or formation of one of the two products. So what would you do if you were tasked with doing that?
This is right here. Oh, formation.
Okay, yeah, but what analytical technique would be yours of choice?
It'd be like,
Sure, in situ NMR is a good choice. React IR. For these types of reactions, NMR is a popular one and a common technique that you'll see for in situ monitoring of phosphine ligated metal complexes is you have this nice 31P NMR signature And so even if other parts of the reaction are messy, then you can track the phosphine resonances and their inequivalent between the starting material and the product.
So as the starting material has a hydride there, so the hydride should appear in a totally different regime, like the proton law as well.
Okay, we will then wrap up the day 5 notes with the last problem of the day and the day 5 chemist of the day. So we have this interesting example. We have a BIP ligated palladium center. We can quickly do our electron inventory on this just to get started. We've got a palladium +2, which is B8. Got 4 electrons. And 8 electrons, so we're 16 electron. D8 square planar starting material. Okay, we're going to treat it with this interesting looking NF pyridinium salt. And the question asks us to propose different mechanisms for this oxidative addition. And we didn't cover that many mechanisms, so 3 is almost all of them. It says propose 3. 3 is pretty much all of them. And then explain based on what limited information you're presented, what you think might be more likely. And then if you want to take it a step further, if you think 2 might be likely, then or all 3 could be equally likely, then how you would design experiments to disambiguate among them. And then lastly, you have in this reductive elimination, what is observed is the CF3 reductive elimination. But if you only consider that any cissoid ligand is potentially viable for reductive elimination, you've got this that you could imagine. You could even imagine instead reductively eliminating one of the NF bonds to make an aryl pyridinium. So why this CF3 reductive elimination? Oh, did I draw this wrong? Sorry. Is the product CF3 Wenji or it's supposed to be CF3? But in the worksheet I drew is F. It is F. Okay, sorry, I got you. Thanks.
The carbon is on the other side after. It did undergo CF3 reductive elimination, but the arrow for concept.
Sorry. Okay, I got you. Thank you. That's what I was confused about. All right. Al, we gotta go to you for this one, I think. Sanford Lab alum. What do you think?
I guess I would think the most likely,
Well, let's just do the mechanisms would be what?
inserted,
Inserted,
then nucleophilic, and radical.
okay, and what did you think was most likely?
I think it would be an SN2 type oxidative addition because of the polarized oxidant that you use.
Okay, so let's just kind of draw out these in cartoon form, what we mean by these inserted SN2 type. And then radical would be like, everybody on the same page. And which one did you say was like the
I
best?
thought it would be the SN.
SN2 type because of the polarized nature. Of the NF bond.
Yeah, that's what I was thinking. Although you can do some experiments to try study this oxidative addition step.
Okay.
Uh,
What other pathway did you kind of maybe consider?
I would think either SN2 type or concerted. And yeah, yeah,
So another question would be, why do you think the other two may be less likely to happen?
the other two.
Yeah, so radical pathway, for example, why would a radical potentially be less likely here?
Um, like, I'm thinking it might be easier to do the electron pathway for that. I guess that arrow pushing it did, than form the lone radical.
Okay. So if you, maybe I can rephrase what you said for you have palladium, so your second row metal.
Yeah.
To go through a SCT pathway is going to involve generating palladium-3, which is, we know in general, second, third row metals tend to disfavor having unpaired. It's more of an energetic penalty to have an unpaired spin for second, third row metals. So that would maybe argue against a radical. And then between the SN2 and concerted,
Yeah. For the
is there anything
concerted,
you dislike about the SN2 pathway?
what I dislike about the SN2 pathway.
Oh, sorry, is there anything you dislike about the concerted pathway?
For that one, I remember from the lecture that concerted pathway tend to happen for non-polar substrates, which is not the case for the NF oxidant.
Okay,
I also want to draw your attention to the steric bulk that's presented by the purity side. Because you have a
Oh,
really
yeah.
heavy environment around the nitrogen. So you end up actually having the triplet not really period that's coordinated to the palladium after the oxidative addition. So I think that's something you can keep in mind. You just do a thought experiment and make sure the transition state of the concerted mechanism. You're going to have a really hard time positioning your palladium at any position of the purity.
good. And I'll stay with you, Al. What about chemoselectivity? CCF3 versus CF versus CN.
Yeah, it was also mentioned that the fluoride and I guess the nitrogen are less polarizable than the carbon in this case, which makes the rate of the CF3 reductive CCF3 reductive elimination faster in this case.
Okay. Any other thoughts on that? Questions? Mike?
Isn't it also, like, if you reductively eliminate anything else that's reversible, you can still oxidatively add it to whatever other bond you'd make?
Yeah, certainly if you reductively eliminated the N aryl, then you make an N aryl pyridinium, and it also happens to be bidentate, so that is going to be, make the transition state more strained, and it would be reversible, so that's probably not a great solution. But the CF reductive elimination is not necessarily reversible. In fact, it'd probably be irreversible because oxidation of this aryl F bond to palladium 0 is a sufficiently high energy that it's effectively irreversible. Pierre, any question?
I was just gonna say on that front that you can also make CF4, which is a gas, which will go away. So
Oh,
that's not a reversible.
that's true. So that is an interesting alternative possibility you could generate. Pierre is saying you could reductively eliminate actually these two. I think in those cases, you just have two very electron withdrawing groups that are, and neither of which is super polarizable, so it's not a great situation. Good.
I just have a question. You mentioned previously that it's more difficult sometimes to do reductive elimination with some of the other heteroatoms like nitrogen or fluorine because the electrons are more tightly bound.
Yeah.
But in the case of a CF3, how does that compare to just a regular alkyl group or another
Yes,
kind
it's
of
also
aromatic?
much
It's
more-
so withdrawn, right? So
Yeah.
how does it compare to some of the other atoms?
Great question. So let's consider just CF versus methyl. So what would you expect to be harder or easier?
I'd expect the methyl to be substantially easier than a
Okay.
CF3.
I agree with that. And why is your intuition telling you that?
Well, I just see electrons being withdrawn away from the CF3 center. It makes it very electrophilic. And I see reductive elimination to be more difficult for that case.
Yeah, it's kind of a similar situation to, you can kind of look at the CF3 and we know this from our experience doing SAR or from doing any kind of like scope. The CF3 is very electron poor. It's kind of, it is pretty inert aryl CF3 bonds, and all of these things are pointing to the same thing, that it's holding its electrons in very low energy orbitals. And creating a strong dipole, molecular dipole away from where you need to form your incipient CF3 bond.
But reductive elimination still happens preferentially with the carbon unit over the other substituents.
It does, yeah. So maybe a comparison I can make here, Julian, is to say, if you were to have this palladium complex where the CF3 was replaced with a methyl, reductive elimination would be so facile, you wouldn't need to get up to the palladium 4 oxidation state in the first place. It would happen readily from the palladium 2 oxidation state. So the trick of inducing this otherwise challenging CCF3 reductive elimination is to get up to palladium 4. To get there, you need to oxidize, but you need to oxidize with something that is going to introduce ligands on the metal, like a triflate or a fluoride, that themselves are not going to get incorporated into the product. So that's the trick to make this challenging reductive elimination possible. That's the kind of reaction design behind the scenes. Mingxi.
So, a little bit on a tangent, but we see that in, for example, phosphine oxidation, actually the reductive elimination can also happen with L-type ligands.
Yeah.
So for example, what is stopping it from reductive eliminating with one of the pyridine ligands here?
Yeah, so this, and this actually happens quite, if we think back to the historical challenges of why aryl F reductive elimination was hard to achieve, a common side reaction was formation of the fluorophosphonium, where any type of phosphine ligand that you would want to introduce actually gets spit out along with fluorine. So that can happen. As I was saying, if you were to do that thought experiment here and reductively eliminate, what do you want to reductively eliminate? The aryl N?
I guess that looks favorable.
You just get to a structure that is also very reactive and it's going to oxidatively add back. So it will end up being degenerate. You can't really do productive chemistry that way. Although there's nothing wrong with thinking that could be possible. Yeah, I always think, you know, if you're ever not sure and you're trying to distinguish among possibilities, you can just engage in that pathway and play it out and see what you make and then try to think through why it would or wouldn't be stable. Okay, yes.
In that case, would you need to use stoichiometric catalyst? Because you would be turning over your catalyst to the original structure.
Indeed. So the example I showed was not a catalytic conversion. It was palladium to palladium 2 complex, converted to a palladium 4 complex, converted back to a palladium 2 complex with expulsion of an aryl CF3 product. So if you wanted to turn over this catalytic cycle, then you'd need to regenerate the aryl palladium that you had just lost, and you could potentially do that. You transmetallate. So I think first pass, you could maybe think about turning this over, but that wasn't the focus of this study. It was just the reductive elimination step.
Thanks.
Okay, we'll shift gears now and talk about various flavors and forms of migratory insertion. The first being 1,1 migratory insertion, which is most commonly, though not exclusively, observed with carbonyl ligands. So let's play this out. We push arrows. Organometallic chemists don't like to push, inorganic chemists don't like arrow pushing, but organic chemists do. We're organometallic chemists, and we can take some liberties and push arrows, I guess. So this is what a 1,1 migratory insertion looks like in terms of arrow pushing. We just play this tape forward. What we have is we're converting one alkyl or aryl metal carbon bond and one bound CO to a new metal acyl species. And we're opening a coordination site. That open coordination site we need to trap with a new incoming ligand, or sometimes the reaction just falls back to the starting materials. So it can in principle be reversible. And so trapping is an important consideration. If we track our ligands, then we see that we had one X and one L type ligand in the starting material. In the product, we have one X and one L type ligand, so there's no change in oxidation state. And that's true of migratory insertions generally. Like we saw before with rectilination, the two ligands involved must be an appropriate geometric relationship, i.e. cissoid, in order to react. We said we need a trapping ligand to occupy the empty coordination site, otherwise the back reaction can take place. Stereochemistry of if the migrating group has defined stereochemistry, it will be preserved during migration by virtue of operating through a concerted mechanism. And then if we think about how to promote this step, one is, or accelerate this step, one is to have a more electron poor metal center. The other is kind of analogous to rectilination. You can have bulky ancillary ligands and squeeze out. It has some analogy to the squeezing out term, colloquial term that we use. The reaction, because you can think of it as having some kind of parallel to sort of like a carbonyl addition, an intramolecular carbonyl addition, that it's enhanced when you have more polarized carbonyls, which you can accelerate through Lewis acid coordination, with hydrogen bond donating ability. We said that the reaction is accelerated with more electron poor metals. So by the same logic, if you increase the oxidation state of the metal through SET oxidation, it likewise promotes migratory insertion. And then within an isostructural series, we see this trend that as you go down the periodic table, when one migratory insertion becomes less favorable and slower. So why might this be? Thoughts on that? Any takers, Sebastian?
Because as you're going down, you have like, these much less polarized metals. So you just have a less polarized metal carbonyl bond.
Oh, that's interesting. So you're pointing to point 3 that your bonding interactions in general, you have softer metals in general, and your bonding interactions in general are less polarized. So that's interesting. I think that's not an unreasonable explanation, but maybe not that I would say is a contributing factor, but not the dominant factor. What do we know about going down the periodic table? We know that metal carbon bond strength increases. So how does that reflect in terms of our observed reactivity trends? We have ground state destabilization as we go 5D, 4D, 3D. Let's say the transition state across this isostructural series largely looks the same, and we're trying to traverse this transition state, and we're starting from here, 5D versus here, 4D, here, 3D. We see the barrier goes down and down. As long as the transition state structure is large, it has similar energies. And a point that I can't underscore enough is that the reactivity trends beyond what I have just put forward to you are complicated. And so there's a lot of things are not hard and fast in this elementary step. Let me introduce a term now called migratory aptitude, which now focuses, we talked about kind of the metal-centric view of this step, and now we'll talk about a ligand-centric view, a migrating ligand-centric view of this step. So what makes a migrating group better or worse? And I like to have sort of a 2-stage triage process here. So the first is to consider the thermodynamics and just ask the question, can this even be done from a thermodynamic perspective? Is it thermodynamically allowed? Is it i.e., is it thermodynamically favored? And if it's thermodynamically favored, then we can wrestle with the kinetics. So what do I mean by that? So there are some ligands, and chief among them of importance is hydride, that will not undergo migratory insertion. In general, there are, of course, for any rule, there are exceptions to the rule, but in general, hydrides will not undergo 1,1 migratory insertion. Why is that? Because metal H bonds are relatively stable compared to the bonding strength is relatively high compared to metal carbon bonds. So we talked about the importance of where you start in the ground state. You're starting too low in a metal H. The ground state is too stabilized to undergo, to end up traversing this potential energy. So there are some ligands that in general, you're not going to observe this step in. So we'll focus our attention on those that do undergo 1,1 migratory insertion, which is the series shown. And we see the reactivity trend is as follows. Tertiary alkyl groups migrate in preference to secondary, that migrate in preference to primary and methyl. And then on down the series, alkenyl, aryl, CF3, alkynyl, acyl, to generate a kind of an oxalyl metal. So this generally tracks with higher migratory aptitude, tracks with increased steric bulk. Decreased MR strength. Why is that? exactly what we just introduced, ground state destabilization. So if you think about an extreme case, like a tert butyl, let's imagine a tert butyl or one atomantal nickel carbonyl complex, then that is an extremely hindered group that's forming a very weak bond to the metal. And it wants to relax from this highly sterically encumbered state. It can do so by migrating the bound tert alkyl group to a place where it is experiencing less steric encumbrance, i.e. through 1,1 migratory insertion. So you start at a higher energy state, you relieve steric encumbrance upon 1,1 migratory insertion, and so those are the key drivers there. Let's take a quick peek at the kinetics, and I'll go through this quickly because I just don't want to get too bogged down in the details. If you have any questions about this, feel free to stop me. So we mapped out in general terms what's going on with the 1,1 migratory insertion, and now we'll just get a little bit more granular, is that we have this initial reversible 1,1 insertion, and then a subsequent trapping step that's drawn here as irreversible. Substrate abbreviated S, intermediate, abbreviated I, product abbreviated P. So if we want to understand the rate of product formation, it's going to be defined as the concentration. So the rate will be equal to the rate constant times the concentration of the incoming ligand L times the concentration of the intermediate I. What's the concentration of the intermediate I? We can use steady state approximation, which if you haven't had a kinetics class in a while or haven't had Donna's kinetics class yet, steady state approximation means that we set the rate of change of the concentration of intermediate I to 0. And then that means that the rate of intermediate formation is equivalent to the rate of intermediate consumption. And then from that steady state approximation, we can eventually solve for the concentration of I, and then we can plug in our concentration of I into our rate equation above, which gets us to an overall rate expression that looks like this. Probably parallels things you have already seen before in your life as a chemist, so I won't go into too much more detail. Let's just consider then the possible scenarios. There are two limiting scenarios on either extreme. The first scenario we'll consider is the one that we will call L always traps, i.e. the rate of the trapping step, which has the rate constant K2. That step is very fast compared to any back reaction. So every time it traverses a potential energy surface of the 1,1 migratory insertion, every molecule that does that is instantly trapped by L. So in that case, this rate equation simplifies. What happens here is that the denominator term is, I'll just show this drawn out here. The denominator term is dominated by the K2L here. So we don't need to consider the back reaction. It's a different color. We don't need to consider the back reaction, and the L's are going to cancel out. K2s are going to cancel out, and this eventually then just simplifies to on pen. So overall rate law then that's just first order in substrate. Then we can do the opposite extreme scenario where we say now the other term is going to dominate. So this one we call almost always goes back. That's a colloquial description, or the more technical descriptions say the rate is governed in the second step. So the K minus one term dominates. So here we're saying effectively this term is so small, we're not going to consider it. And then relatively so small. And then the rate equation simplifies. This. And then the other extreme, so those are the two extremes. And then everything else is basically the rates are sufficiently similar that nothing cancels out. This doesn't have a special name. It's just nothing cancels out. And that means you need to consider both steps. Okay, let's take a look at problem of the day number one. And this is this one from the day 6 worksheet. This one I think can be a fast and furious one. So I'll just give you 30 seconds to think about it. I'll do a quick screen share just in case you don't have it handy. I get all these pop-ups and then I can't actually get to the window I'm supposed to be sharing. That's what's happening right now. Okay, so pretty straightforward. We have this acyl pentacarbonyl manganese complex, and we've labeled the carbon of the acyl group. It can form the product shown A and B, and you just have to predict and then rationalize which one is forming. What do you like here? Anna, A or B?
I feel like it's A.
You like A. Okay. So walk us through your reasoning to get here. What happens first? You lose a CO. Which CO did you lose?
The axial.
So this we'd probably call axial in this context. Is that the one that you lost?
Yeah.
You lost this one, okay? Thanks. Okay, so you said axial, and to me, in this context, axial would mean this one, axial with respect to the acyl. Is that what you mean?
Oh, I was thinking the one on the top.
Okay, yeah, let's use the
Oh.
cis or trans
Cis.
nomenclature. Okay. So these four are all equivalent, right? So they're, you can pick one and it's the same as picking any of the other. So you'd like losing this CO. And then what happens next?
Elimination.
So now you have a retro 1-1 migratory insertion, i.e. alpha elimination. Bring you alpha here. Here. And that puts your label then here. Happy? You don't look happy. You're happy?
If I get your big dry, I'm Because I cannot imagine how B can work.
Okay, well, that's a good reason to pick A then, if you can't imagine any way that B can be found. Good, anybody got anything different? Everyone follow the same logic? Great. This sets the stage for the step that Anna just taught us, alpha elimination, i.e. retro 1, 1. Also sometimes in the context of CO chemistry referred to as a decarbonylation. Let's consider, and I don't want to walk through all the same reactivity trends and how to promote because it's literally just the opposite of what we just covered. Let's just get into a specific example here. We're going to start out with Wilkinson's catalyst, and then we're going to put it in solution, and it will do this mysterious thing Oliver was asking us about of losing a ligand in solution. It can do that. What happens next? You open a coordination site. We'll just take a, yeah, what do you think? Incoming is acetaldehyde.
It's the CH insertion.
CH insertion. Okay, so the first step will be formation of the sigma complex, and we will not draw that just in the interest of time. You said you're going to do a CH insertion, which also you might want to refer to as an oxidative addition. And in this case, there'll be a minor geometric reorganization that I won't say too much about, but I'll just note. Chloride does not want to be in those trigonal basic positions. So it will slide to an axial position. You make this acyl. What next? Yeah, let me stay with you here.
I think it's alpha elimination.
Alpha elimination. Now we have a CO ligand and we have our methyl. And then get us home. What's going to happen next?
You have the elimination of methane.
Loss of methane. Formation of what is the final product?
It's for coordination without H and methyl.
Formation of, and again, another kind of minor geometric reorganization here is that if they can help it, phosphine ligands don't like to be cis to one another. Sometimes they can't help it. So like in the Wilkinson's catalyst starting material, they've got to be cis to one another. If they can help it, they prefer not to be. So that's what will happen here. Beautiful. So this is, you just outlined the elementary steps for a name reaction, Suji Wilkinson decarbonylation. And so this looks great, but then what if I told you I ran this reaction and it's not turning over catalytically? What would you say is the problem? I converted my aldehyde to my desired alkane, but it's stuck. It requires one equivalent. Yeah, Eugene.
Because you still have that CO ligand on there at the end, so you need to replace it with PPH3.
I think did you actually run this reaction? Yeah. Before?
Yes.
You have. Okay, all right, there you go. And was it stoichiometric or catalytic? So you ran it catalytically?
Fail.
It failed. Okay. Did it work stoichiometrically?
I don't think so.
No. We published papers where we can only do this stoichiometric. So it can be done catalytically, but you have this problem. You got a CO ligand, your metal center is relatively electron rich. CO, of course, pi accepting, so it's forming strong bonding interaction. And you need to get it off and replace it with triphenylphosphine. So that's your problem. So how might you do that if you needed to get the CO off? Heat it up, that's reasonable. You know, Barry Sharpless once in a talk said heat is the best reagent. And so there's no problem with running a reaction at 160 degrees because heat is the best reagent. Now, I think we could debate the merits of that statement, but that is what he said. So you heat it up. The idea is that even if this equilibrium, let's play this out here, even if, here's kind of the problem that, let me just rephrase what Eugene said. So here's effectively your issue is that you have an equilibrium that lies really far in the wrong direction. But Yao was saying, if you just heat it up, eventually you will make some CO, and then the advantage is because it's a gas, it will leave the reaction vessel, and through Le Chatelier's principle, you can drive it. So indeed, this is why some catalytic Wilkinson, Suji Wilkinson decarbonylations are run under quite forcing conditions. What other strategies could you imagine? Yeah, Sash.
Are there ever examples where you could add in basically like another sacrificial metal that just kind of mops up carbonyl and makes, just a bunch of carbon?
Love it. Yeah. CO, some kind of CO scavenger. It could be a metal, could be an organic reagent. Did you have something, Will?
I was thinking maybe not for this substrate, but could you also run the reaction under like strong vacuum to try to pull the CO out of solution?
Yeah. You got to make sure to not pull everything else, but
Yeah.
vacuum, static vacuum, there are ways to do this to push the equilibrium. Light, we talked about photo dissociation of ligands. You could use light to photo dissociate CO.
Can we just use more phosphines or use a stronger phosphine?
Use more phosphine, that is reasonable, but you do have to be concerned then about your equilibrium upstream. Because you got to lose phosphine to get on cycle, but then you're going to need to gain phosphine to close the cycle. So that's your challenge.
Here is a small typo. The second to
Please.
last time, you're evolving methane instead of CH.
Thanks. Thanks. Not methyl rather. Great. Okay, we'll take, I want to be in trouble for this. I think this one can be fast. Okay, let's just take 2 minutes. We'll do this as a class. And then we will just wrap up and run right over to the defense. So the question is, you have this interesting neopentyl tantalum olefin complex. And I'm telling you that it is in equilibrium. So this can happen sometimes. It's kind of interesting. You see a shape-shifting organometallic complex. There are two similarly stable versions of its connectivity. Sometimes these can be described as interesting to think about how to describe them in terms of isomers. You can think of them as linkage isomers or something like that. So what is the structure of C and how are we forming it? Alex, did you want to volunteer a thought?
So I think it's the tantalum alkylidine with the neopentyl. And I don't think that, so it's either the tantalum hydride or that will also insert into the olefin and then give the tantalum ethyl alkylidine.
Brilliant. Okay, so I teed this up by doing the electron count. If you count this out, you'll see you've got 2 chlorides, an alkyl, so tantalum 3+. That gives you a D2 metal center. You've got 1, 2, 3, 4, 5, 6 ligands, 14 electron counts. You can imagine this is a pretty electron poor metal center, not super happy, reactive. And Alex was saying what he likes here is we're gonna take this suggestively drawn H. We're effectively gonna do like an intramolecular oxidative addition, but we're not gonna call it that. I'm gonna delete that because I don't want to don't want you to call it that. So we have effectively like our alpha elimination here. And Alex is saying this could be the product, or this could just react further. Now you have a situation where you have a hydride, you've got a bound olefin, and that is a recipe for what we will cover next time in more granular detail, which is hydrometallation in its microscopic reverse, beta hydride elimination. So if we track, this is what's happening to the H atoms. And this also sets the stage for the topic that we will cover, is how to do electron counting and how to think about these metal carbon multiple bonds, in this case, non-kilidine, in this case, a Schrott carbene. That term, if you haven't heard it before, is not really meaningful to you. But we'll leave things here and pick things up next week. Have a great weekend, everyone.